Bismillahirrahmanirrahim. Welcome to network analysis. This is the new topic we are going to start on Easy Learn. And before going to proceed, because this is the episode 1, let's define some rules of this course. In this course, I specially designed this course only for beginners. Means those who are they think that they don't have enough knowledge or capabilities to learn anything. I will try to explain even very basic steps. Even if you say two charges, addition of the two charges, even I will explain that too. So which means that this series will be gonna be the largest series on Easy Learn, and so hopefully you like it and you appreciate these efforts. So this is all for you, and your suggestions are always appreciated, and I will always try to the duration of these episodes, I will try to limit in the 20 minutes, maximum 20 minutes, and minimum 15 minutes. So this is the lecture duration which I decided for dedicated especially for this series. So any other suggestions, I will always appreciate this, welcome these suggestions, and let's start, and further discussion will be if anything come in my mind, and if any ideas I will be adopting day by day if in the meanwhile. So in today's discussion we are going to start from the basically charge. It is the discovery. Thales of the Greece is credited with the discovery. That is actually a mistake, sorry. This is 600 BC. Thales of the they are credited with the discovery because at that time when the briskly rubbed with the piece of the silk, when we're going to tightly rub, not simply rub. Here you can I use the word briskly, means tightly rubbed. We're gonna use the piece of the two things. First, silk or any fur. Let's suppose silk, piece of the silk cloth, rubbing with the amber becomes electrified. Amber become electrified. Okay, two things are we are going to rub: silk with the amber, and then amber will become electrified, and when it is going closer to the pieces of the threads of any clothing, then what happens? They are going to attach with the amber. Then the Thales of the Greece, that's basically the reason they noticed this thing at that time, 600 BC. So at the beginning of the charge starts when this thing is noted at that time, means the attraction force. What is the behind this? Why at that time they are basically shocked that this is like a magic, but there is always a science. Okay, so the amber becomes electrified and the capable of attracting pieces, small pieces, not very large, because small electrostatic force. So we are going to discuss all the things in details. This same technique for the production of the electricity was used centuries later, right now, not even now, but centuries later, and still before us, in the Coulomb used these techniques. Now we are living in the modern age because we have these developed formulas, but we are talking about a little bit history that Coulomb then used. Later on they are get modified and added something, further discoveries, and finally the Coulomb in the French scientist basically is given the credit, and also independently by the Cavendish in England in establishing the inverse square law of attraction. This is the Coulomb basically developed the theory on the inverse square law of attraction bodies. The inverse square law of attraction bodies, this is especially term used in the scientific language or physics especially. Any law which is directly proportional of the two quantities relation and inversely to the square of the distance between them. So same is the case Coulomb used. So we can say like Coulomb basically used that this is suppose a charge and there are two charges. The attraction and repulsion between these two charges is directly proportional to the intensity means if if it has intensity of the 5, suppose 5 coulomb intensity, if we increase its intensity to 10 coulomb charge, then definitely there a force of attraction or repulsion. This depends upon the like charges or unlike charges. If they are like both are positive, then they may be they are definitely going with the repulsion, because they are like charges. Never mix up this. Okay, if they are opposite charges, always attract, and they are according to the Coulomb, they are inversely proportional. Their intensity is inversely proportional to the distance. Means if we are going to increase the distance, this is inversely proportional. Not only inversely proportional to the distance, but the square of the distance. This is called inverse scale laws of attraction bodies. So this term is used in the network analysis. On the present day, understanding of the nature of charged bodies is based on the conceptual scheme, that is modern scheme. We are now living in the modern age. We are based on this scheme that sometimes we called simply the model, planetary model. Like we are using this, suppose this is the sun, these are the orbits of the different planets, sometimes called planetary model. This is the basically nucleus, and there are electrons in the outer shells. In each shell there are specified formulas to calculate how many electrons can be in the maximum in each shell, and we discussed all the things in the season 1 of Introduction to Electronics in details. You can go to this section and easily find out the stuff whatever you want relevant. Right now we just want atom as composed of positively charged, as I represent here. This is the atom. Okay, so atom is here composed of positively charged particle, and these are the electrons, these are negatively charged. And how much negative charge, how many positive charge, overall you simply in atom there are basically protons and neutrons. Neutrons, remember that, and N stands for neutrons, and remember that from N carry, N means no. Okay, so no charge. P is equals to positive. P is from P, abbreviate the positive, and so P is equals to positive charge protons. So if there are 10 electrons, means 1 electron 1 negative charge, 2 electrons 2 negative charge, 10 electrons suppose, so 10 negative charge, just for the assumption, then it means that there are 10 positive charges, 10 protons in this, because this is a balancing state. In the normal position the atom is in the balanced state, but if in case if there are a number of the electrons, suppose I just with the help of any energy or in the excitation state, I just give it energy or any bonding happen, then the electron leaves, then it will become an excessive positive charge, because in the nucleus there are the equal number of charges, positive charges. When a deficiency of an electron happen, then there is no change occur inside the nucleus. So it means that overall this is an excessive of the positivity happens in this overall atom. It becomes a positive charged. Any substance, not particularly this atom, any substance with the excess of the electron is called negatively charged. This happens when it accepts an electron mostly, because it sometimes they are the donors and sometimes they are acceptors. If this electron is going anywhere, this is not the waste. Someone will be here to accept this. So this one basically excess of the negative charge, more electrons are coming in the shell, which means the overall result is the excess of the negativity. So let's go towards another thing, that the basic key units. MK system means standard system, mass kg and second systems. This is the standard system used, and for basic unit of charge is the charge. If the basically we discuss the unit of the charge is simply the charge of electrons. Like if the electron has suppose one charge, then charge of electrons is the basic unit of the charge. Simply, what is charge? Charge basically come from the flow of the electrons, that is basically current overall. We are discussing one by one in details. Charges is the combination of different charges on electrons. Charge is on electrons, not charge specifically is a term that is appended on the electrons, cannot explain without electrons. So MKS unit of charge is Coulomb. Coulomb is a scientist who is responsible for the discovery, and that's the reason behind him that he was named after naming the unit of this. He was just credited because so we always remember his name whenever we're going to discuss the charge. Electrons has a charge of 1.6021 into 10 raised to power minus 19 Coulomb. C stands for Coulomb here. And never forget about this term. This must be on your fingertips. This is the first episode, so we are going to use this again and again. This must be on your fingertips. 1.6021 into 10 raised to power minus 19. Remember, this is you make sure you have a plan for watching the episodes. Watch one episode daily, but remember that whatever you learn, you note down it in your notebooks, and always remember that, because this is easy things. We are going to start from the beginning and going toward the modern era in the details of all the things that engineers demand. So hopefully you are going to learn this thing in your notebook right now, even if you know too, because sometimes we forget about things. I forget about things. So we are humans, not the computers. Okay, the phenomena of transferring charge from one point to another point in a circuit to another circuit is described by the term called electric current. So this is the time we are going to define the electric current. What is the electric current? Whenever we are going to transfer the charge from one point to another point, this means the flow of charges. Simply, it is called the current. But remember that here one thing must be kept in mind, that if this is a cross-sectional area, some charges are flowing randomly here. This is a movement from this point to this point, but this doesn't mean that this is overall a current. The net effect of this is zero, because some electrons move toward this side in the cross-sectional, some randomly move this side. So if one electron go toward this side, the efficiency is filled from here toward this side. So randomly, this is the net overall effect in this metallic piece. It is zero. If all the electrons are moving, very minority charges are moving against this, then the net effect is there is a net overall flow of the charges. So we can say there is an electric current. And one thing is that is the transferring of the charge. An electric current may be defined as the time rate of the net motion of electric charges across a cross-sectional boundary. What does this means? Means that electric current is the time rate of the net motion. Remember, net motion, overall effect with respect to time. This is I is equals to dq over dt. This is the derivative term. Basically, derivation means change. We are going to enter into the new term. This is a formula. Write down in your notebooks. I is equals to dq over dt. This is the I is the current. D over d means this is the change. Whenever we are going to use derivative, it is understood that there is a change. Change is very important for the current. If there is no change, current is zero. Net effect, overall net motion must be net motion. Okay, time rate of the net motion of the electric charges move across a cross-sectional boundaries. Cross section, this is the boundaries, this is the boundary, and this is the distance between the boundaries, and their net motion of the electric charges across a cross-sectional boundary. Random motion of the charges in a cross-sectional area of a metal does not constitute to a current unless there is a net transfer of the charge with respect to some time. So let's go toward some mathematical calculation, and before this let's give some credit to the French scientist Ampere, who is the who is often called the founder of the science, father of the electrodynamics, and founder of the science of classical electromagnetism. He was basically French mathematician and physicist. So, okay, on his name we are going to use the current in measuring in amperes. If the charge q is given in coulombs and the time is measured in seconds, the time is measured in the current is measured in amperes. Current is going to be measured in amperes, charge in q, time in seconds. So these are the units. Ampere, A-M-P-E-R-E, Ampere. This is the name of the scientist, comes from, we are going to just use A for the simple terms, charge on one electron. So here mathematics start. This is what I told you to write in your diaries. So again, recap the previous slide. Charge on one electron is equals to, we discussed one point, suppose this is the atom, these are electrons, so this is the electrons. Charge on one electron, we discussed 1.6021 into 10 raised to power minus 19. This is what we discussed a little bit earlier. Did you remember that? So if you forget, so recap, go back. Okay, just going to simplify this using mathematical steps. One electron, just one electron, charge on one electron, just skip this. One electron here, one need to be remembered, one electron is equals to 1.6021 into 10 raised to power coulombs, means this time of the coulombs. If we need to find 1 coulomb carries how many electrons, so we need 1 here. So moving this towards the other side of the equation, towards left hand side of this equation, this is the equality sign. This is multiplicating with the, means in the numerator and the upper side of the equation, you can simply side, it will say that here it is in the multiplication with the c, and by going to the other hand side it is in the denominator, it will go into the denominator. Then I am writing it 1 divided by 1.6021 multiplied 10 raised to power minus 19 electrons is equals to 1 coulomb. So 1 coulomb is equals to, by dividing all of this, we got these 6.24 into 10 raised to power 18 electrons. 1 coulomb is equals to, so remember that also. But if you forget, simply use calculator, and because our brain sometimes we are going to use tricks. So simply 1 divided by this is the number of electrons that are in 1 coulomb. So we are going to now use this term 1 coulomb. Remember, 1 coulomb is equals to what we use, okay? So which means that according to this definition, that if this is a cross-sectional area in 1 second, okay, so define this formula, dq over dt means that charge will be 1 ampere. This I means charge will be 1 ampere if in the cross-sectional area there are 6.24 electrons. These are the number of electrons we discussed in the previous slide. So these 6.24 into 10 raised to power 18 electrons, not only 1 2 3 4 so 5 6 7 8 9 10, not these, means 6.24 into 10 raised to power, means these amount of electrons. These are just 10 or 20 electrons I can just mention here, but imagine 6.24 into 10 raised to power electrons if pass in 1 second. In 1 second, time duration is 1 second, pass through a point, through a cross-sectional area. Suppose this is a cross-sectional area right now for us. So at this cross-sectional area, if this cross-sectional area, we have a stopwatch here, counter here, and we are checking that how many electrons are coming from here and passing through this cross-sectional area. If 6.24 into 10 raised to power electron pass through this cross-sectional area in 1 second, then we can say this is the current of 1 ampere. Okay, so this is by the definition. Basically here dq means charges, and I'm going to replace the charges with electrons by the conversion in the previous slide. So the electrons, these amount of electrons with respect to time, 1 second, time duration is 1 second. If time is 2 seconds, then we are going to convert this equation in this same pattern. Here everything is 1 ampere in 1 second. If in a 1 second the double number of the charges go through with this process, then the current will be 2 ampere simply. Okay, so this is the end of episode 1. Hopefully you like the efforts, and we are going to continue the topics, same topic in the next lecture, because I had decided that the maximum time limit for one lecture should be 20 minutes, and that is enough, I think, for understanding. And one episode in one day, you try to go through with it, and make a routine of watch every one episode in one day, and learn something in your highlight the points in your diary, so that when we go to the next episodes, when we're moving to the higher episodes, these basic things are in your mind, so we are not wasting the time again and again repeating the things. Okay, so take care. Allah Hafiz.